Our next topic introduces something we've already mentioned several times so far, and that is transformers. The way a transformer works is you've got a coil, and you can have another coil here. And so one coil has N1 turns, the other coil has N2 turns. And so as current is flowing through here, it's producing a flux. The total flux that it puts through there is going to be related to the number of turns there. So the total flux will be proportionate to N1. Okay. And so that's going to be here. Now for the other one, the total flux through there is proportionate to, so I guess proportionate to N2, because it's got N2 turns. Okay. So now we know that the EMF induced is minus the rate of change of the flux. And so what's happening is that if this current is changing, so in other words, that di dt is not equal to zero, if the current is changing, then the flux is changing. And so the EMF is going to be related to that. Now the EMF per loop, okay, is going to be proportionate to the EMF per loop, and then we multiply that by here, but each one has this number of turns. And so the end result is that we end up with current going through here. Now, what's going to happen is that the current going through the secondary is often moving, going around in a different direction of the coils because, remember Lenz's law tries to minimize the change. Okay. Now, so what do we get out of all this? Well, in an ideal situation, then we know that the electrical power going here has to match the electrical power over here. In other words, this is transferring power from there to there because we got current flowing here, we got some kind of power supply over here, we might have a load over here. So the end result is from the fluxes, we realize that that for our coil here and another coil, what we often do is we actually, rather than wrapping the other coil around there, what we often do is we will wrap the coil around an iron yoke. The iron yoke actually connects both coils. So we wrap the other coil around that yoke. And so the magnetic field induced here goes through there. And so it actually shepherds virtually all of the magnetic field through there. And so that means there's very little wasted field flying around elsewhere. And so we get the maximum amount of flux to the secondary coil. It also means that the iron actually amplifies the effect. And so it makes it stronger. So that's good. Now, in a perfect transformer, the power in here equals the power out over here. Now, in reality, we end up vibrating the molecules in the yoke and heating it up. And so there's actually a little bit of energy loss. But in an ideal transformer, power in equals power out. Power in is going to be on we call the driven side, so the side here, the primary coil, and the other that's connected to the load, the secondary coil. Okay, and so we got the primary and secondary coil. So that means that I primary, voltage primary has to equal I secondary, voltage secondary. Okay, now there's also going to be a phase factor in there, but it should be the same phase factor for both, so that cancels out. All right, so we could then that and say the voltage on the secondary is I primary over I secondary times the voltage on the primary. Okay. Now, here's the interesting thing. We know that the primary and secondary fluxes have to be the same. Well, the flux is the flux because of the way that the capacitor the transformer is working. We're shepherding all the flux through here. So the flux is going to be proportionate to the current, and it's going to be proportionate to the number of turns. Okay, so we could then say that the I primary in primary has to equal I secondary in secondary. Okay, because they got to be proportionate. So if we use that, then I primary is I secondary in secondary over in primary. And so we could then add into the equation above and say voltage of the secondary is equal to the N of the secondary divided by N of the primary times voltage of the primary. Okay, so if the secondary has fewer turns than the primary, so in other words, NS equals NP, then that would imply that VS is less than VP. In other words, the secondary has less voltage. So this is what we call a step-down transformer. On the other hand, if NS is greater than NP, then that means VS is greater than VP, and that is a step-up transformer. So what does this mean? A step-down transformer you're probably more familiar with, because the step-down transformer is what you use in the phone charger, for example, or in any other transformers you typically have around the house, and that is you got 120 volts coming in, and it steps down in order to use a lower voltage. Step-up transformers you rarely see in the home environment, but in an industrial environment you would sometimes need much higher voltages, and so you can have a step-up transformer. Or when you generate electricity, you normally generate it at lower voltage and will step up the voltage, and so in that case you'd use a step-up transformer. So this is the basic idea of transformers. Now, should also point out that transformers can have other interesting properties, and that is that if you have a power supply right here, and the symbol we use for a transformer is actually this, in which we have a coil on one side, a coil on the other side. So that means that we're going to have a current right here and a voltage right here, but that you also have a current right here. You have a resistance here, so that means the voltage on the secondary is going to be I secondary times R, right? Well, I primary is not going to equal I secondary, typically. And so that means that this will act like it has an effective load over here, okay? Because you're going to have current flowing here, and so that current, it's going to, if you just look from over here, if you just look at the circuit here and don't see what's on the right hand of that circuit, it looks like there's a load over here. That load is not going to equal the load resistor because the currents are not equal. So that means that we ought to be able to figure out what's called the reflected impedance or the effective load impedance. And so we'll do that in an example problem.